Hello there and welcome back to this video series on control systems. So far we have been seeing topics on time domain analysis such as Routh's criterion, root locus method and analyzing response through time domain analysis. In this we have seen several topics such as Routh's criterion, root locus method and techniques related therein for analysis and design of control systems. We are going to shift gears and look at another method which we call frequency response method. As a part of this analysis, we are going to see topics such as what is meant by frequency response and specify advantages of frequency response methods and what are the two ways of plotting the frequency response data, and these questions we'll try to answer in this video. Perhaps you'll be able to do the same at the end of watching this video. In this analysis we use complex numbers quite a bit, and so I would strongly encourage you to watch this video 043 before you get into this video. When we say frequency response, we mean that the input R given to the system is a sinusoid with amplitude Rho and frequency omega. A unique feature of linear time invariant systems is that when you give such an input, sinusoidal input, and wait for sufficiently long period of time, after this long period of time we say that the system has settled down and we are measuring at steady state. Okay, steady state output is also a sinusoid. If the input is a sinusoid, you can keep applying the input and you wait sufficiently long period of time. The output represented by CSS, steady state output, is also a sinusoid with the same frequency but with a different amplitude and a phase shift. We are interested in two aspects here. Okay, what is the ratio of this CO to RO? We call it magnitude ratio. And what is this phi? This we call it phase shift. So we are interested in these two. We can graphically show them here. Let us say this is the wave RO with whatever amplitude. You apply this wave to the system and you wait sufficiently long period of time and then notice this output. The output is shown in blue form. To be specific, we have used CSS of T. Okay. Two things we are of interest is what is happening to the amplitude ratio, that is amplitude of this blue line to that of red line. That is what we are interested, and we are also interested in what is happening to this phi. As you keep on increasing omega, what is happening to this ratio, what is happening to this phi, this is what we are interested in. For each value of omega, what is CO by RO and what is phi? This is what we are interested for whole range of frequencies ranging from very small values to very large values. We say omega tends to 0 and omega tends to infinity. At this point we may want to ask the question, why are frequency response methods important and why we need to study them? One solid reason would be that any given function can be expressed as a summation of sinusoid series using Fourier series, and thus if you know response to sinusoid, theoretically you know response to any other function. Also, frequency methods allow us to analyze time delay exactly without resorting to any approximations as needed in the case of time domain methods. And there are very many graphical methods available for analysis and design of systems using frequency response methods. A beautiful aspect of frequency response method is that this frequency response data can be obtained from experiments. You can either mathematical analysis or directly from experiments. And there are two methods, the Nyquist criterion and Bode plot. These methods which exist in the domain of frequency response allow you to define some magnitude of stability, that is gain margin and phase margin. And also, once we have data, experimental data of a system, a sinusoid frequency response data, we can infer the transfer function of the system. That is one excellent feature. Then frequency response methods involve measurements at steady state. Because they are at steady state, the burden on instrumentation is less, because you don't need very fast sensing of data. Typically, when you say frequency response data, this data comes in the form of a table as shown here. You have frequency in one row, magnitude ratio CO divided by RO in another row, and phase angle in third row. You may have them in 3 columns. It really doesn't matter. Okay, this table is what we mean when we say frequency response data. There are 2 ways in which you can represent this data. One is what we call polar plot, and the other one is what we call Bode plot. Each feature has its own, each plot has its own features, which we may say are merits, demerits. We are going to see each one of them in a little bit in the slides to come. We'll begin with polar plot. The same data, how to represent in polar plot. You set up real imaginary axis and draw a line with angle phi 1, this angle, okay, and on that line set up a length m1. At the tip of the arrow, identify the point. Once you do that, you have represented omega 1 m1 phi 1 set. Then perhaps you can erase them and complete the other point, that is, draw a line making an angle phi 2. On that line, draw a vector with length m2. At the tip of that vector, locate a point. And so on, you repeat for all the other values. You may have 5, 6, 10, whatever be the number of frequency values. You represent that, and then you draw a smooth curve through all these points as shown here. This constitutes polar plot. One thing that may be slightly confusing for you is we are using the symbol omega for frequency as well as imaginary axis. All the textbooks follow this notation, which is slightly confusing, and so we just follow it. But just remember, when you see omega on the S plane, real and imaginary axis, this omega represents imaginary part, and then frequencies, when we talk of frequency response data, this omega represents frequency. Once this plot is drawn and you get away with this table, there is no way in which you can infer the value of frequency from this graph. For example, at this point, what is the frequency? We don't know. Okay, that is one downside of polar plots. So on the polar plot, you need to explicitly indicate the frequency, even to infer the direction in which the graph is going. Okay, this particular graph is going from very small frequency values here to very large frequency values at the end of this plot here. At any intermediate point, you have to indicate the value of omega to explicitly specify it. Otherwise, looking at the plot, you don't know what is the value of frequency. With that said, we will look at the other way of representing the frequency response, that is Bode plot, and then perhaps summarize this video. When we say Bode plot, it actually means two different graphs. One is omega versus m graph, another is omega versus phi graph. Let us show them both. It is the same frequency response data. You set up this axis. At omega is equal to omega 1, draw a line. At m1, draw a line. They represent a point. Similarly, at omega 1, draw a line. At angle phi1, you draw a line. Phi1, you draw a line. Locate a point. And so on. You repeat the same for all the points on available in this data set. Okay. You locate another point, locate another point, locate another point, and so on. That way you get a set of points for omega versus m graph, and you get set of points omega versus phi plot. Once you obtain these points, you join them with a smooth freehand curve. Once you do this, you say you have drawn Bode plot, omega versus m and omega versus phi. Okay, these two plots they are drawn with omega axis here and omega axis here on a semi-log graph sheet. Omega as log and m in decibels, that is 20 log to the base 10 m, along y-axis in linear. Because you are drawing logarithm on a graph sheet, you call it semi-log graph sheet. You have graph sheets which are log-log graph sheets. We are not using them in this context, but omega as a logarithmic scale and m in decibels, you draw it. Okay, this plot, these two put together, is what we call Bode plot. To sum up, we say that these Bode plots and polar plot put together frequency response plots offer certain advantages over time domain methods. We have seen why we need to study frequency response. There are perhaps 6 distinct reasons, and this polar plot can be plotted either as this frequency response data can be plotted either as a polar plot or as a Bode plot. An important feature which we have not seen yet is that these frequency response methods allow us to quantify stability in terms of what we call gain margin and phase margin. At a subsequent point in this video series, we will try to see what we mean by gain margin and phase margin. I think that's all we have for now. Have a great day.